Good morning, and welcome to the Nuclear Materials Fast Pitch session. Today, we have three exciting talks. We'll talk about fusion. That's the first talk that I will be discussing. And my name is Ahmed Diallo. I'm Program Director at ARPA-E. The second one is going to be Dr. Bob Ledoux. He's going to talk about metrology. And Jen Shafer is going to close it out with Langtonite recycling. And the talk is Let Me Upgrade You. So, I just want to say, just to remind you, you can send using the QR code the questions, and then we'll answer it as we go. Okay, so again, the race for a working fireplace and a good match. So I like to use this analogy. At the end of this talk, I want you to take a couple things in mind, walk away with a couple things in mind. First, we have fusion. We know how to do it in a controlled way. Now we need to move on to the ancillary part, which is effectively moving to the fireplace. As we do that, we want to think about a good match and a decent fuel, or if you want like something we can produce, mass-produce a fuel. So let me remind you, for those that are not familiar with fusion, fusion powers the universe, and how does it work? It's basically light element that you've merged together, and effectively they produce like a slightly heavier one, and then you have energy that comes out of it as a byproduct. So the energy of the universe has been used to power the stars. Now the goal is to kind of bring it to Earth and then use it as an abundant source of energy with light element fuel. Now, fast forward, what are the benefits? Well, technically, in principle, when you get working, it will have zero carbon emission. It will be dispatchable. It was powered down, and actually, it will be it will provide low-level radioactive waste. There's no runaway issue with fusion. And actually, you can think of fusion energy as being like a civilization-scale energy. Now, there are two challenges you need to do as you think for your fireplace. You need to ignite a little spark, and that is done with light element, and energy comes out like I discussed earlier. But then again, you need to move to the next challenge, which is sustaining it. So those are the key challenges we need to address. So luckily, last year, we were able to have a controlled fusion ignition. And that was achieved at Lawrence Livermore National Lab. It was the first of humankind. Let me walk you through this. Basically, the 192 laser beam were focused in a little canister that contained a fuel that is about the size of a ballpoint. Then basically, the laser ablates this canister and then gets like enough X-ray to compress the fuel, and it continues compressing until you get full compression and ignition. Once you have the ignition, you generate about 3.15 megajoule. That was a 1.5 gain that was achieved. That was good. That was spectacular, major breakthrough. Now, we know it was done. It was done over a few nanoseconds. But the next big step is like, how do we make it more routine? Okay, so now you take this 3.1 megajoule, and you can think of it, it's about 60-watt light bulb that you light up for about 14 hours. Now you take this, just like a cartoonish power plant would be something like this. Basically, you get the ignition that occurs. You want to get a blanket that takes that heat out, some sort of heat conversion, and then you heat like water or another liquid if you wish. And then you get process heat from that, and finally you go to a turbine generator to put electron on a grid. One of the key things we need to work on, and we need to keep working on, where we need to innovate, is the fuel, how much fuel you put in, as well as the heating system, because it eventually would take the electricity back and feed into the heating system, and we want to make sure they're efficient. So, sustainability of the ignition requires engineering, and there are major challenges. So, technology challenges remain, hence we are here for the innovation, and I want to draw the parallel with a fireplace. You have the fuel, that's the log, the little fire match that will give the ignition, inject the ignition, and the material. So, for a fusion power plant, that amounts to effectively having a good fuel. But the challenges are very clear. we can't mass produce this fuel target. It costs a lot. I can't even get a price tag, but it's more than 20,000. You produce that once every few days or maybe months. Then we get to have a low, right now I want to challenge low wall plug efficiency systems for the heating driver, and the rep rate is low. We need to go to about a few times a second. Right now we're about once every hour. And then finally, the whole containment should be material that are resistant to high heat flux, for instance, and to be irradiation tolerant. So let me start with the fuel target. This is a little picture of, courtesy of Lawrence Livermore, of the fuel target. It's a cartoon illustration of what really is happening during the ignition as the laser goes through the hollow. This is just an example. So ideally, you would want to have like high gain, meaning like high quality fuel, so that you achieve like at least 60 times of what you put in. And then the cost should go down to about $1 per target. And we need to be able to get to about 500,000 daily production of these, so that the power plant can continuously run with minimal downtime. So we're not quite there yet. So in terms of the match, which is a heating system requirement, one can think this, what you're looking at here is the inside of a tokamak, which is another concept, for example, where you need to be able to continue powering your plasma here and dumping heat into it. But to do so, we know how to do that, but you need to have effectively an efficient system. So right now, if I take, for example, a heating system that we have in a magnetic fusion, for example, using microwave, they're about 40% efficient. And ideally, you want to go to 70. That may require a paradigm shift, given the limitation. The reason why they hit 40% has to do with thermal management. The lasers, right now, if you think about it, during the experiment, it was really sub 1% efficiency. We need to back it up to 20, to go up to 20%, and then do a higher rep rate. Those are major challenges that require innovation. That's why we're here. Now, last but not least is the fireplace, the containment. So these fireplaces, the containment here, this is a vessel from Joint European Tourist. What you're seeing is like metal tiles, some are tungsten, others are beryllium. And they will be sustaining extreme environments, something that no material has seen as you build a power plant. Extreme temperature, 800 C and above, and heat flux is 10 megawatt per meter square. And actually, the thing that is really the killer is neutron that is about a 14 MeV, but high flux, 10 to the 18 neutron per second. So, no material have seen this. And given that we want to have a fusion power plant that could last long, or have uptime that is 90%, innovation is required. That being said, this is really where we need you, innovators. The plasma physics has been dealt with. It's not complete, challenge remain, but now we need to move to the other part, which is defect-free, low-cost fuel, efficient heating systems, material for extreme environment. You can think of like get some alloying to get there. And I'll call in everyone. It is all hands on deck, given that this can become the civilization scale energy. That being said, tomorrow we have a breakfast with us. So I invite you to come talk to me. We have ideas. Bring your ideas, let's talk. Don't be afraid. Talk to me. Thank you. Next, I would like to introduce Dr. Bob Ledoux.
Thank you, Ahmed. It's a pleasure. I'd like to begin by, I'm Bob Ledoux, I'd like to begin by welcome you again to the ARPA-E Summit. And I would like to speak to you today about not a common topic that we speak about at ARPA-E, but about metrology. And I would like to begin with a quote from Lord Kelvin, who said, if you can't measure it, you cannot control it. And I think that is the simplest statement of the importance of metrology, the science of measurement. And the premise of this fast pitch is basically there's been such a rapid innovation in metrology. I think we practitioners looking for energy innovations need to catch up. And how best do we do that? The specific topics I would like to speak to today, since this is the nuclear session is innovations in metrology for the rapid development of the nuclear materials, much like Ahmed just mentioned. Now, to give you a powerful example of the importance of metrology, I'm going to go give a little history example here. So around about the end of the 19th century, we had a theory of light. It was Maxwell's equations. But the question was for scientists, like, what was it a wave in? So they postulated the luminiferous ether, some mechanical basis for light, and a prediction of that would be that if you move relative to it, the speed of light would change, right? That was the abiding theory. The question is, could you measure it, and was it true? And at the end of the 19th century, the answer was no, you couldn't measure it. But Michelson, of Michelson and Morley, took an interferometer and actually refined it so that it could find the difference in the apparent speed of light of the Earth moving through it. And okay, we all know, did they measure a change in the velocity of light in a vacuum? No. No experiment that turned the scientific community on its head. And it led 15 years later to the special theory of relativity, which again, we would never look back on space-time in a different way. And now I want to go 10 years later than that, and then we get general relativity. And in the ensuing 100 years, we've done many tests of special relativity. You probably got here with a GPS, which has a general relativistic correction. But the most important, really, prediction of general relativity is gravity waves. And in this case, metrology took 100 years to catch up with that. And just recently, the LIGO, another interferometer, has actually measured gravitational waves. But get this, it needs to find a displacement to 1/10,000th the diameter of a proton. So I think we as human beings should be proud of that achievement. So are we at a tipping point? Now I'm going to concentrate on materials. Are we at a tipping point because we have the ability to measure over previously unattainable lengths and timescales? And can we all in this room leverage that even faster so that we can do our own innovations? So you cannot consider measurements typically without a model or a theory. So where is this dance at the moment? I would say models and materials, we have good quantum chemistry calculations and we have good computational capability. However, there's holes in that, which we're trying to supplement by machine learning and AI. The point is to bring even the models forward, we need new metrology because we need to inform those very difficult cases. And so I'm just going to give two examples in material development for nuclear. I'm just going to concentrate on two metrologies that have had rapid advancement. Atomic level 3D imaging and atomic attosecond, it's a very small number, trying to take snapshots at the time scale of chemical processes. And this is one of my favorite figures. This is relatively new. This is from UCLA and Berkeley Labs group. This is the first 3D measurement, there's a rendition of it, of the actual atomic structure of what they wanted to be an amorphous metallic glass. So the very first thing that metrology is making a difference in, if you have a new material and you make it, is it what you wanted it to be? And the answer in this case is mostly yes. It did turn out to be an amorphous glass. However, they also found some other structure in it. And whether that's important for structural materials and so on is to be seen. Now I'm going back to Ahmed, who talked about special materials that are needed for tokamaks. And on the inner plasma-facing wall, he gave you all those conditions. Just like tons of neutrons, high temperature, stress, and strain. On the right of this figure is one of the first atomic level imaging of an alloy. And what was even more important about this measurement is that not only did they image it, then they stressed it, they put a strain on it, then they looked at what happened to the alloy, and they did find changes in it. If we want to make new materials, we need to know what we made, and we need to be able to test them faster, and this atomic level imaging is great for it. Now my next example is from nuclear fission. We want to make a new waste form. That's going to be exposed to radiation for a long time. So how do we know a material that we make is useful for that? So this is a beautiful 4D measurement. I'll explain 4D is not time and space in this measurement. And what they did was really quite remarkable and beautiful. This is from a Los Alamos group collaboration. What they did is they imaged the material, then they applied dose to it, then they imaged it again, then they actually annealed it, and then they imaged it again. And what they found, remarkably, what you can do in this case, It was not done in situ, unfortunately. That's another talk. But what they found was remarkable structural changes when they went through that whole process. And the 4D in this case is both the transmission imaging combined with the diffraction. Enormous amount of data comes out of these measurements. Now I'm going to turn to another dimension, time. And, you know, we really don't have a way of seeing atomic chemical reactions. But we know, you know, historically, remember, it was fascinating to actually see, you know, horses gallop when film first came out. We have strobes and so on. But at this point, attosecond timing, 10 to the minus 18 seconds, we are now reaching the point that we can take sub-femtosecond pictures of materials and their properties. And this is one of the first measurements of an electron cloud, actual material, essentially being seen over the time scale in which that structure changes. So the goal, I think that, you know, the absolute promise of this is that what would be unlocked if we could actually stimulate something, a photoexcitation or so on, or a catalytic process, and then actually watch it evolve in time, dynamically see it evolve. Not only will we learn about that particular thing, but this is the kind of data that the models need to have to push forward from their sort of static rendition of chemical processes. And finally, I'd just say that I'm not sure what a tricorder is or was, but what I do know was handheld, and every science officer had one. And besides making these new metrologies, we have to be absolutely sure we get it into as many hands as possible. And further, we need to be sure that as much of that data for our purposes is public, it's curated, and it's going to be giant. It's got to be placed someplace. So this brings me to a call to action for this august group here in this room. And that is, how do all of us, given the situation, the rapid development of metrology, how do we view our role with it? And so I think there's three non-exclusive categories we can consider. The encourage is the organic process. We know about it. We expect people to use it. Hopefully enough people can use it. And in a certain sense, we've raised the state of the art. Exploiting it, though, is different. I don't think ARPA-E has explicitly done this, which would be, let's take a problem like dose in materials. Well, let's find a better source of neutrons. Let's put it in situ. Let's do the imaging, et cetera. Basically, do both the metrology development along with, say, the materials development in this particular case. And the third, which I think it's extend this, is there a metrology in which, you know, that rising tide would lift all our innovative ships in a certain sense? That is there something big enough that basically if we had a project, you had a program in it, that it would be useful to everybody? And I think there are some candidates for that, maybe another talk, but I'd love to continue this discussion both tomorrow and going forward. That's my contact information, and I hope to hear some of your great ideas and continue it. And now, it is my great pleasure to introduce my colleague and fellow program director, Jenifer Shafer.
Thank you very much, Bob. You know, a lot of the measurements that Bob was alluding to earlier really tie into the topic that I'm going to be speaking about today. And, you know, Ahmed, I'll connect to your presentation maybe a little bit at the end of the talk. But one of the things that we might be aware of in the room is that it's actually Women's History Month. And last year, I gave a pitch on reprocessing technologies, and my pitch was actually named after Madame Curie, or I should actually say the program that has come out of this. And sometimes on social media, we might have seen that Madame Curie is referred to as Mariah Carey. Now, the question in my mind was, is there a way that I can evoke greatness in this way, in this fast pitch? And I think that you've seen, as Beyonce would say, let me upgrade you. So how this connects to is I'm going to be talking about rare earth recycling and basically upgrading post-consumer materials such that we can use them effectively to push our clean energy transition. So when it comes to critical materials, we know that they have significant importance to this, whether this is batteries, wind, solar, nuclear. We need minerals and materials to push this transition. And what I'm going to focus on is actually rare earth materials, in part because it's a significant part of my technical background. So let's go ahead and look at this a little bit more. It turns out that rare earth materials, and why we think about them, is we know that rare earth demand is actually going to triple by 2040. We also know that, for example, you can think about 600 kilograms of rare earth materials being present in a single wind turbine. We also know, and maybe this is something that's a little bit less known, is that actually when you mine, mill, and recover rare earth materials, for example, you leave actually, for every 1 ton of material, you leave behind 1 ton of radioactive waste. And so there's actually an intersection between clean energy technology and rad waste materials that are being generated on the back end. And we also know that this is going to enable a multi-trillion-dollar transition. And so what I'm going to be thinking about today is how can we push this transition more sustainably and more economically. So where are rare earth elements? Well, here's a periodic table here. It turns out they're towards the bottom, and many of them. Now, my favorite elements of the periodic table are actually on the very bottom, but we'll spend a little bit of time just here. So the ones that are really important for our clean energy transition are basically yttrium, praseodymium, neodymium, terbium, and dysprosium. And you'll also notice that several of these elements are right next to each other. And this actually creates some very interesting chemical challenges that need to be addressed, because it turns out that for the lanthanide series, the lanthanides all have very similar chemical properties. And as a consequence of this, this actually makes their separations very challenging. How do you separate things that are very similar? So as a consequence of these tough separation challenges, there are some environmental impacts that come about because the separation, frankly, is not this efficient. And we actually saw Dr. Evelyn Wing talking about companies out there in her preliminary address to us all that are trying to improve the sustainability of rare earth mining. And so we know that this is a critical thing that needs to be addressed. So when we think about mining practices and production practices, many of them happen overseas. About 90% of rare earth production occurs in China. And one of the things that we look at is, as a course of basically crushing, leaching, producing these materials, you end up with significant acidic lakes that are produced from this process. And so here's a picture of one in China. And it turns out that this lake, if you were to drive across it, is actually about 10 minutes long to drive across. So these are substantial consequences of basically environmental practices of rare earth mining. And I'm here to say that it doesn't necessarily have to be this way. And if we could actually improve these practices, we could do it in a way that would be more economic and perhaps enable us to process these materials more stateside. So the question here is it possible to develop more sustainable and economic separations from post-consumer materials? So to do this and have this conversation, let's back up a second, think about, how does nature help us? So nature actually has some really great properties about it as far as how just weathering and erosion and environmental chemistry happen that enables the co-location of minerals to form at a single place. This is why we have mineral deposits. And so it turns out that there are some places on the Earth's crust, courtesy of all these environmental factors, that generate these types of deposits. So basically, the Earth's surface is a big elemental concentrator. Now, there are two mineral forms that are particularly relevant for rare earth production. One of them is bastonite, and the other one is monazite. I'm actually going to be focusing on bastonite here. So when we look at bastonite's elemental composition, it turns out that you have things like calcium, carbonate, magnesium, barium, sulfate, oxygen. These actually comprise the majority of your bastonite. When you actually go to recover rare earths from this, you're looking at the order of just a fraction of this is your lanthanum, cerium, and then even smaller fractions are your neodymium and praseodymium, which are really some of the critical minerals that we were looking at earlier. So how does this look if we're starting to think about post-consumer electronics? So what about e-waste? Well, it turns out that people have thought about this, and they've taken iPhones and thrown them in blenders and crushed them and done all of this to evaluate what is the elemental composition of your iPhone. And it turns out that a lot of it is hydrogen and carbon, basically plastic, a significant portion of aluminum, and then you have other things like oxygen, iron, and silicon. Well, okay, what happens to the rest of it? So we actually have lithium, copper, cobalt, chromium, nickel, magnesium, sulfur, and we actually still haven't gotten to the rare earths yet. We have to actually expand our slide a little bit. It turns out that there are more elements in your iPhone than are actually necessary to drive the workings of the human body. It's an incredibly complex technical machine, for that matter. It turns out that neodymium and praseodymium are right here. and an approximately 1/36th and 1/79th the concentration of what you would actually have originally in the Earth's crust. So this is not great from a separation perspective, but we're on the order of about 10 to 100 orders of magnitude, and we are modern chemists and we can think about this differently. So when we think about separations, and I was pointing to earlier, right, these elements are right next to each other on the periodic table, it turns out that there are a handful of dials that you can manipulate to push this forward. One of them is size, so if two elements are of significantly different size, this makes a separation easier. The other one is the orbital availability, so if two elements have significantly different orbital configurations, you can manipulate chemistry from this perspective. And then also redox potential, so if you can shift the oxidation states of elements relative to each other, this is another great separations handle. So when we look at the lanthanides, I've already beaten the point to death that, well, they're about the same size. When it comes to orbitals, it turns out that the f orbitals contract within basically the shell, your electronic shell of the atom, and so they aren't particularly available. And we've got redox. Well, it turns out about all the f elements are trivalent, so which one of these are we going to push on to make this happen? I'm actually going to focus on redox in a little bit, but I will get there. So the industrial state of the art, so we've got praseodymium and neodymium separated by 1/100th of an angstrom. It turns out that we use state-of-the-art 1959 technology to drive this separation forward, a molecule that I'm very familiar with, bis-2-ethylhexylphosphoric acid. So we do this using solvent extraction separation. So basically, we have oil and water when we partition lanthanides from one phase to another, and we do this 7 times. And when we push this separation 7 times forwards, we end up with about 92% purity of our neodymium and praseodymium and only 3% recovery. And so as a consequence of this, we need to do this multiple times, hundreds of times to drive this separation forward. And we end up with significant waste on the back end of this. And actually the production yearly is anticipated to be something on the order of just about a Great Salt Lake a year by the time we hit the maximum of what we need to do for our clean energy transition. How can we do this better? Well, it turns out when it comes to nuclear fuel recycling, we've thought about this a little bit. And americium and curium also are separated only by about 1/100th of an angstrom. And it turns out you can actually oxidize americium to the hexavalent state. It takes about 1.7 volts to do it, so it's not easy, but you can. But when you actually do this, you do your oil and water separation. Now you only need to do this 1 time instead of hundreds of times. And at the end of this, you end up with 92% purity, 99% recovery, and now we're talking waste on the order of swimming pools instead of Great Salt Lakes, right? And so this is much more cost-effective and to manage. Can we do the same thing for the lanthanides? Well, it turns out perhaps. Praseodymium and neodymium shown here again. We can see that we can actually oxidize praseodymium to the tetravalent state, but now we're at 3.0 volts. This is non-trivial. This is ARPA-E hard. Well, it turns out that there are a couple of people that have actually thought about this. So we've got Pete LaPierre at Georgia Tech and Mariana Mazzanti, actually at ETH Zurich, that have come up with a couple of different molecular compounds that show that we can actually oxidize some of these critical materials to the tetravalent state. And once we have them oxidized in solution, maybe you could actually push separations from this. And so really when it comes to thinking about rare earth opportunities, I think that we could spend more time thinking about the redox question. And I would love to talk to you more about separations or Mariah Carey. Oh, and I promised that I would connect to Ahmed's talk. So for a period, there was concern that I might be the only person talking about singers here. And I maybe mentioned to Ahmed that I've got a great idea for fusion. And the idea was, I've got 99 problems, but ignition ain't one. So we look for, so we'll turn the floor over here. Thank you all.
Thank you, Jen. I think we're going to move to the Q&A section. So the first question that came in is for me is, can you elaborate more on the composition of exit streams in fusion processes that makes it low level? So I refer to low level about mostly had to do with the structural material that are mostly alloys. As they interact with neutron, they get radioactive. Depending on the choice of the material composition, one can have a set of alloys that will be less radioactive. So that also forces us to think outside the box as we develop these alloys, basically to make sure they're not radioactive. That's an extra criteria that needs to be added in developing these novel alloy. Now, in a fusion stream, effectively, that's even that's even lower level radioactivity because you have tritium. You don't burn all the fuel. You have tritium, deuterium that comes out, and then sometime you take, for example, a fusion process such as MFE, you would have effectively some gas that you inject to kind of basically a buffer gas to reduce the heat load on the plasma-facing component. Those will come out and you go to a tritium processing plant, and then it gets filtered and then refed back with the deuterium back into the tokamak. Now, for IFE, of course, if you do the horum, there's other composition that will interact with the tritium, and then that would have to go through a stream and then get reprocessed. So overall, what I meant is the structural portion of it that needs to be taken really good look at when you develop an alloy. I hope I answered your question. The next question is for Bob. What are the prospects for massively distributed and democratized metrology? For instance, cell phone apps.
What's the last one?
Cell phone apps.
Cell phone app?
Yes.
Okay, I'm not sure about the cell phone app on this because basically there's a massive amount of data that is taking place in this. Okay. So I didn't give you a feeling, but that 4D imaging, I think a few runs of that is a terabyte.
Okay.
And so basically, I think that it becomes a big data problem even to collect that. And I think the greater problem is who's collecting it.
Yeah, that's right.
Where is it? Who curates it? Mm-hmm. Right? Not every, and I should say that a lot of the things I showed, they are based on COTS, off the shelf, very fancy instruments, but a lot of the ones I showed basically were modifications. So they're kind of one of a kind. And of course, if they are successful, they will be exploited. But I think we can assume that the data that comes out of these is large as sort of any other data sets we've ever seen. So I'm not sure. It's not sure it's going to be a tricorder story.
So I'm gonna wait for people to keep entering their question, but I would like to ask a question to Jen, actually. So one of the questions is chemical separation the only way to separate rare earth elements?
No, and so actually this was a great point because I was thinking about some of the presentations earlier this week. Chemical separations are not the only way you could do it. You could actually do this using physical-based separations, temperature, things of that nature. And so I'm a chemist, so I have a little bit of a myopic view with respect to that. But yeah, you can get at this some other ways.
Good. All right. There's another question for me. What about DPA? So I didn't want to bring that up here. Yeah, DPA is important. It's really the key metric here. I need about 20 to 50 DPAs, I think, for a fusion power plant material. So that's important. But having 14 MeV, that translates to DPA, which is actually displacement per atom. Your neutron goes and displaces the atom and then makes them brittle. So these need to be folded in developing new alloys. So we don't have a model, a full understanding what's the process with neutron knocking all the atom and then how they make it brittle. But I think one of the things that I would like to focus on, I would like people to think about is, can we basically use other means to infer what will happen when you go to 50 DPA or even 100 DPA as we move on to a big fusion power plant with 95% availability.
Ahmed, can I say something about that?
Yeah, sure.
So one of the things I was talking about, general extending technologies. Right. And I think both in fission and fusion, it is a shame that in this country, we don't have a number of sources of 14 MeV neutrons to test these materials. And I think that's a metrology. And I would further point out that the ideal situation would be if fusion and fission are so important to not only improve the metrology, getting a source of well-defined collimated 14 MeV neutrons, but also in situ, irradiating those materials you want to use and dynamically imaging, measuring them as a function of the displacements per atom. I think that could revolutionize what materials can be chosen, because I do worry that things like superconductors and so on that you have for magnets, you don't have a choice on what elements you use there. So we need to understand that.
Great, that's a good point. Thank you. Jen, there's a question for you. You showed example of lanthanide-based rare earth separation. Mm-hmm. Are lanthanide-based separation cost-effective, and are they sufficiently stable to be recycled?
Oh, so the idea that for kind of the next generation, the higher oxidation state stuff, would that actually be cost effective, and can you actually do it? So this is something that would have significant challenges with it if we were actually to push forward on this, right? For some of those examples that I was showing, I mean, these are being managed in no oxygen environments, right? So they're in glove boxes, basically. But that's kind of where we can figure out how to push the chemistry. So maybe this could be the fusion of rare earth separations, right? There's 99 problems with this as well, as far as trying to stabilize it. Once you actually have it stabilized, could you actually extract it or phase transfer it? I'm much more familiar with some of the americium curium work that was done. And there were things there that once you actually did try and push this separation forward, you have to be very deliberate in managing that chemistry and monitoring it. So this is in no way ready for the showroom floor, but I think the idea is if you could get it to work, the capex of your facility might be substantially decreased, right? Your waste management costs would probably also be substantially decreased, right? And so that's kind of the idea that, maybe you could push in that direction and get it going.
Thank you. I think I would like to follow on a little bit on what are the wastes that are contained in rare earth element that can be separated.
What are the wastes from rare earth materials, right? So there are a couple of different things that can be recovered from the rare earths. Actually, funny enough, one of the things that is sometimes treated as a waste byproduct, but I know some people have interest in it, is thorium, right? So thorium is something that is co-located with rare earths, but some people will point to that and say, oh, this could be an excellent material for nuclear power, right? And so there's a couple of different components there that you could consider. So
cool, very nice, thank you, Bob. How big are the current measurement tools that can measure atom? How big is it?
Oh, okay. Actually, they're modest in size. I mean, they fill a large room. It's usually an electron beam with its optics. So I would say, it's just like, a meter, a couple meters and a few meters tall. However, it is in a vacuum, and I would say that equally important is the preparation of samples. So I would say that to do this right, it's actually a lab. But it is not, the electron, the atomic imaging I showed was not large. Light sources is another issue if we get to, but those are large.
So there's a question that came out. It's like, what do you see the role of AI and computational advances in nuclear energy production? That's a good question. I think I would like to break it down into a small aspect, actually. I would say for discovering new material, that will play an important role. I mean, we are at a phase where we have done enough modeling, but enough. I mean, we could still improve on for the element we know that we can expand and then seeing what next element we should be discovered, at least expand the search phase space. In terms of operating, I can tell you, for example, AI has been helping in terms of operating a fusion reactor, for example, an MFE, a test reactor, for example. They use AI for controlling. That has an advantage. The rest, everything that's balance of power plant, I'm not really sure where are things, but I would say that it would have to play an important role as we move on, because we can't control everything from first principle, and we need to kind of relax a little bit that constraint and use AI to kind of project us to a commercial power plant.
I was going to say, I think that this could almost be a good panel question. Bob, do you want to go next? Or?
Well, I was just going to say that, I mean, in nuclear, both for control and design, I mean, right now, the difference between a lot of the new advanced reactors is that their fuel is not in one position. The assemblies are not stationary. They move and so on. So even though these very high fidelity neutronic calculations that you could have the luxury of spending a long time to do, they may become much more dynamic.
Okay.
And so I think at least a dimensional reduction model or machine learning and so on will have to ultimately maybe inform a direct knowledge of burnup. And I bet you that Jen may have something to say about O&M and Gemini.
Yeah, so basically when it comes to nuclear energy production for advanced reactors, ARPA-E has a program, the Gemini program, that was launched by Rachel Slaybaugh. Bob and I basically manage components of the program. And really what it does is it uses AI machine learning approaches, digital twin technologies, if you want to call them that, to drive down the operational costs of our advanced reactors, or I should say the projected operational costs of advanced reactors. So there's lots of different ways that we can think about this. This could be enabling predictive maintenance strategies, i.e. the idea that if you're actively monitoring something and it seems like it might be time to take it offline sooner rather than later, you can actually do this as a planned, scheduled maintenance, right? When nuclear reactor power plants go down for maintenance, it's on a very set schedule. So they basically design everything around the outage to take care of as many things as possible. And if you think that something needs to be addressed sooner rather than later, right, this can have a significant impact as far as minimizing unintended, basically interrupted power production aspects. And then there are other aspects that you can think about, as far as safety and security and other matters. So AI machine learning is really going to be very central into how advanced reactor technologies deploy moving forward.
So I'll take this one for Bob, and then I'll come back to you and myself. So this question on DOE BES has invested billion into XFEL and neutron source.
What?
XFEL? That's free electron laser, I'm assuming.
Oh, free electron laser.
Yeah. And SNS, which is neutron source. ARPA-E awardee could be user of these, but how can this instrument and technique be developed, which often requires a lot more funding?
Yeah, that's a great question. And I think that the general question of light sources in general, free electron laser, one way of getting there, but also you can do Compton backscatter. I honestly think of the one metrology that could really change everybody is to get the accelerator technology, the laser technology, to make coherent monochromatic light sources that can come from things like that. That if you could make those, I mean, we have like an advanced light source, but it takes months to get on it. You have to make an end station. That's one of the democratizations, is that I think that with the work for BES, maybe even we leverage it in the future for specific application, like maybe a high energy light source that's very compact. Right. I think that might be a mutually fantastic program.
Right. And just to even amplify, Bob, I have a hard time thinking of an instrument that could be more impactful than a compact, coherent light source. Yeah. The idea that those could just be at every chemistry department, national lab in the nation, right?
Might be really revolutionary.
Right.
Good, thank you. So I have a question for me. Is like, what are your thoughts on the prospects of achieving self-sustaining fusion reaction, I guess, or is a pulse mode good enough for practical power generation? So I can tell you, for instance, IFE would have to be pulse mode, okay? And it would be good enough if they can get to the few hertz or greater than one times a second in terms of repping the laser, the drive, and the target. There are concepts where to do pulse mode. There are concepts I want to do CW, meaning continuous, and those concepts I call like stellarators, for instance, where basically you turn on the power, the reactor, and you keep it on if you can self-sustain that. So yeah, I think both concepts are really viable, and depending on which path you use. One path, for instance, I know in MFE, you don't tend to burn up all the fuel, and it's more of a integrated system, which is more challenging to build and to operate. While it looks like the IFE system where it could be a lot more modular, so one can work on different components and reassemble that. And yet again, you still need to have it integrated, but you don't have to integrate it from the get-go. So I would say I'm open. Both are really plausible, and I don't pick any winners here. We want to see energy on the grid. So either way, the fastest will be the greatest one. Thank you. I have a question for Jen. How about low-rate, low-energy processes building on concept like uranium chelation for seawater schemes?
So just in general, the idea of, with respect to uranium chelation for seawater, right, it's just, I think you were saying it's low rate and kind of low throughput. I mean, so there's a lot of different ways that you can kind of skin this cat as far as throughput and processes and how you want to absorb CapEx cost and things of that nature. And so when you're looking at critical mineral recovery, in this case, thinking about uranium recovery from seawater, there are lots of things that you kind of have going for you in that instance, and that one of the things that can add significant cost that would be actually a challenge in post-consumer materials is just actually crushing the sheer number of iPhones, right, that you need to take care and manage and recover the rare earths, right? Whereas uranium, one thing that's really interesting about uranium is a lot of times minerals actually basically form solids at the bottom of the Earth's crust or the ocean, but basically for uranium, it's actually soluble in carbonate media, which is basically what the ocean is. And so there's already actually a pre-concentration step, if you will, of uranium relative to other minerals that might be out there. So that's one thing that you kind of have going for you. Now, to the question, the person's question or kind of observation, right? This ends up being, though, a little bit more lower throughput or kind of lower maintenance, right? And so that there are different ways that you can kind of leverage that. I think on some level what we had seen that is perhaps been a challenge in kind of moving this forward is, we started looking at this when uranium prices were really quite high, was kind of the catalyst for pushing this forward. Depending on what happens with the uranium market, this might be something that we ultimately re-examine. But another thing that I would be remiss if I didn't point out is there are excellent uranium resources sitting in our nation's used nuclear fuel.
And Jen, isn't there a panel on that today?
Actually, come to think of it, Bob, I think that there is a panel on that today. So
3:30.
3:30. So Dr. Ledoux and I will be hosting a panel looking at management of our nation's nuclear waste and some opportunities and technical innovations that could be enabling there. And we will consider many things. One of them may be thinking about recycling the material.
Absolutely. It's already sitting there.
Thank you. There's a question here for me is like, should advanced neutronic fusion fuel be of equal focus? Do the benefit of eliminating the irradiation problem outweigh the additional challenges then put on the driver and matches? I think that's a very good question. I mean, I'm torn all the time. I would love to get like an electronic fusion power plant, and we can just toss out the material issue out the window, or at least minimize that. However, the driver is an issue. You need like to really heat these fuel at much higher temperature. Never done. It's very difficult. And then you have other problem that could kick in. For example, proton boron. You would have like a Bremsstrahlung that's going to kick in. So this is research that needs to be put forward for sure. And I would like to see a lot of people focus on it in terms of research area, both in IFE and all the other concept. But we're not quite there. So finding a driver that can ignite these other fuels would be very interesting. So I keep the door open. We need to innovate in drivers. It's not specifically for DT, but I would say that keep in mind that if we need a paradigm shift for driver, that could help us really get the driver that provide higher heat for the fuel. So effectively, I'm open, and this is something I'm not closing the door. It's something we'd like to see pursued.
And it's fair to say there's some companies pursuing it.
There is, ARPA-E Energy is pursuing this, and that's something that is that was at the forefront of the company at the moment. So there are other companies for HB11, and there's in other countries. So I would say definitely, I'd like to see more people doing this. This is a question for Bob. What are the biggest hurdles to implementing advanced metrology processes into commercial facility to monitor processes such as vitrification processes?
Yeah, I think it's cost. I think it's basically,
Cost.
I think it's still a cost driver. And as I said, it's not just the instrument, it's everything it takes to control it and so on. Yeah. And a lot of the things, as I said, are in vacuum, very small samples. You have to process the samples. You have to transfer the samples. So, national labs, big university labs, and so on, they can do all of the pieces of it. But to democratize it, I think that is maybe a program to make it simple to do. Yep. And maybe you give up something, spatial resolution, but you make it much easier. So I think that's why I'm excited that in conversations here, maybe there are programs that don't have to push the envelope everywhere, but get it into more hands. So I think it's a great question. And it's like any new technology, there's always a trade-off between performance and cost and availability. Right. So I think it's a fantastic conversation to have. Yeah.
Well, and even to that point, Bob, I think, when we think about people managing and handling samples, to what you were saying, right, this can end up actually being a significant cost, not only in the aspect of, the fact that you're paying somebody to manage and control and prepare the samples, but also just in the throughput of your assessments, right? So to the degree that we could perhaps leverage things like big data, AI, machine learning, to kind of leapfrog this and get that, I think that would be
fantastic. And as you learn more, you have to do some less things.
Right.
but in other areas, but it sets the stage for knowing what to do next. So it's a great idea. And the data part, I think, is absolutely central to this, to make it useful. Yeah.
So I have a question for me here that has to do with what about constant wave laser, LEDA? Sorry, I don't know this, and that's for you to tell me. Maybe tomorrow you teach me a little bit. I don't know what that is. So there's a question for Jen. How does the total amount of rare earth contained in all our recycled electronic compare to the amount needed for the clean energy transition? Will new mining still be needed to be part of the solution?
Oh, this is a good question. I mean, I think, right, so even just to a first approximation, you could make the argument that the rare earths that we have recovered, right, and deployed into our, so that is enough to kind of sustain what we've had to date, right? So this is kind of one thing, and actually we run into this in iron and steel a little bit when we think about decarbonizing this industry, so sorry, this is a little bit of a tangent, but one of the big ways that we're decarbonizing iron and steel is actually by doing scrap recycle, right? This is a much less emitting process than actually going forward and just making new iron and steel. But we have a tendency to grow as a world and as a humanity, and we have still needs. And so there is still actually a need for primary iron, and you can't just kind of scrap recycle your way out of it. And so that would kind of be my first approximation when it comes to rare earth recovery, is you could still get some significant benefit from actually the recovery of these materials as far as the amount of mining that you would need to do. But I imagine just because we are having incoming demands with respect to the clean energy transition that you would need to do mining now. The general chemistry that I was talking about, though, could actually still have a significant impact on even mining operations. There's nothing that says that we would have to use that chemistry in just kind of a post-consumer way. And so there's a lot of different ways that we could actually make improvements. Dr. Wing was talking about companies looking at microbes, and that has benefits because now you're not dealing with acidic streams, right? It's a much more benign process. So we will probably still need to mine our way to accomplish the clean energy transition, but I think that there are ways that we can do it more sustainably. So.
And could I just add something? Because our other colleagues at program directors at ARPA-E are thinking about more circularity in things like batteries and so on. So I guess the question would be, if we're putting so much rare earths, I don't know the answer to this, but out there, if we're putting so much rare earths in things like a turbine, motors, et cetera, could we help the problem by designing it at end of life? Recovering those rare earths is trivial.
Right.
Make it so much easier just to get, now that we know it's a problem, to engineer it in, take it out.
And I guess now that we've kind of alluded to him, I'll go ahead and say this. So this is Laurent Pilon is starting to look at this and looking at ways that we can improve economies of circularity and things of that nature, and basically designing for end of life. And actually, I think that there are kind of two benefits that could come from his program. One is just the easy plug and play, right? Maybe you're able to recover something and deconstruct it very efficiently, and maybe what you're able to actually deconstruct, maybe there were other components that went bad, but you're able to put back the component that's still good, right? Yeah. And so that's sort of the dream, right? But there's also other ways that probably in the way that you would be designing this and improving it that would actually even simplify the separations that you might need on the back end, and so making just general improvements to the challenges there. So actually I see a lot of intersections with how thinking about circularity at the design stage could make significant improvements with respect to waste management.
Yeah. We're all over the place.
We're all over the place.
We're all over the place. So there's a question for all of us, actually. What do you view as the role of government in commercializing advanced reactor? I'm assuming advanced reactor and fission, probably.
What do we think the role is?
Yeah, the role overall.
I think it's very important. And we haven't.
As government people.
Hey, we're the government, and we're here to help you. I think it's crucial. I think it has to not pick winners as much as possible. Absolutely. But I think particularly in early stage things, since it is a complicated endeavor that has not always had a positive learning curve, I think the government at all levels, not just the nuclear, advanced manufacturing, all of it, if it came together, I think could make a tremendous impact. And from our end at ARPA-E, we've had the MITNA program and so on. And all our programs are basically trying to help advance reactors. And I think the government role, because it touches so many places, we don't do policy, but it touches policy and so on. I think the government's role is absolutely crucial, although the heavy lift is industry. But our role in getting them rolling and so on, going through regulatory, I think we play a significant and should play a significant role. But that, no policy.
Yeah.
No. And I agree with you, Bob, just as far as, we've already seen some significant benefits from, and actually they were talking about this yesterday on the main stage, not necessarily this particular example, but, how government can be enabling and getting some of these early stage technologies de-risked such that industry can really get to a point where it can take over. And it's no secret that nuclear is a very capital intensive industry, and this can be a lot for people to absorb, finance, et cetera. We've seen great examples within the ARDP program with respect to X-Energy and TerraPower and others that are actually in the process of being able to be deployed as a consequence of this. And I think one thing that we've already even seen from some of our efforts with respect to Curie and onwards is when it comes to waste management, there are more people coming and looking at the commercial opportunities in this space, and so more entities considering there. And so to the degree that government can actually provide basically a kickoff mechanism to industry, right, that's a really critical role.
Yeah.
So I would like to add also for Fusion. For instance, Fusion has the recently announced milestone-based program for Fusion, whereby the government helps fund some of the fusion concepts that want to have a roadmap toward commercializing fusion energy, and that's kind of really some milestone-based. So they have to meet some sort of milestone, and from there on, they get reimbursed. That's really critical for fusion energy to go on the grid and to have electrons on the grid as fast as possible. So that's, I would say, definitely the government will play a role, not forever, but at least to get things going. And then once electrons are grid, I think this is all the private industry that's going to be selling us the energy, basically. So at that point, everything can be from the industry part of it, and they can try to push through. But, we still fusion is going to be around for a while. Like it or not, there will be other concepts that are going to be developed, so we need to kind of still continue looking at other concepts. These are the mainstream concepts that we know, we're aware, that have been studied for a long time. Once they go over the hump by putting electron on the grid, they'll transition to the industry, but there will be other concepts that come in with maybe compact, right, more dispatchable, maybe 10 megawatt type fusion concept that we haven't thought about it. So, but at least once we have one crossing the line, there will be a lot more coming, and that's the government needs to help them. So, I think that we are almost close to an end, but I would say that there are a couple questions, but I would like to get some thought from Jan. It's what about precious metal recovery from spent fuel?
Yeah.
How does the market compare to rare earth?
Right. Okay. So when you're thinking about recovering platinum group metals from from used nuclear fuel compared to rare earths, the prices don't even compare. I mean, when you look at we have about 90,000 metric tons of used nuclear fuel in the U.S., and within that, you have about $60 billion with a B dollars worth of platinum group metals in there. On that basis alone, you could make the argument that we could be thinking about recovering and mining our used nuclear fuel just for the platinum group metals. When you compare the rare earth recovery from spent nuclear fuel, I think it's on the order of only a measly $250 million worth of material there. So, so that's it's definitely a resource that could be considered from that perspective.
Thank you. This is good. So I have a follow-up question for you. Let's just say fusion is there. Fusion gets you to 14 MeV with a high flux. Would you think that transmutation of material could lead to production of these rare earth material?
You would get even more, Ahmed. You would get more platinum group metals because it turns out that they actually sit in the valley of the mass distribution curve. And so 14 MeV neutrons, you could probably even get double. So you would have about, $120 billion worth of PGMs. You'd end up with about the same amount of rare earths.
Cool. That's a good segue to toward the end. I would say, first of all, thank you to the speakers. And this is the end. We're wrapping up, and I would say, come meet us tomorrow if you have further discussion. You can see in the hallway. But thanks for your participation here.
Yep. Thank you.